We have been solving assignment number 4. And we have solved problems 1 to 5. So, we now solve problem number 6, which says consider a long cylinder with its axis on the z axis. So, we have a long cylinder, so that fringe effects are gone, with its axis on the z axis. It is made of a dielectric material of electric susceptibility chi e. If it is put in a uniform electric field E equals E 0 y, find the electric field, polarization and displacement in the cylinder. So, if I look at it from the top, if I look at this cylinder from the top, what is happening is, here is a material chi e, and we have put it in a uniform field going in the y direction. Now, from experience, we know that this is going to generate a uniform polarization inside. And what does this uniform polarization do? It creates in turn an electric field in the opposite direction. It creates an electric field, which I am showing by yellow, in the opposite direction. So that the net field inside is a combination of the applied field and the field which has been created. So, let us say that the polarization created is P in the same direction as E. So, this is P in the y direction. This in turn will create an electric field E, which is minus P over 2 epsilon 0 or minus P over 2 epsilon 0 in the y direction. So, that the net field inside E is going to be E applied, which is E 0 y minus P over 2 epsilon 0 y. Now, I can find P using the constitutive relationship, which says that P inside, since everything is in y direction, I will not bother to write the vector sign on top, or let us write it for the timing. P inside is equal to chi e epsilon 0 E at that point. So, this is going to be equal to chi e epsilon 0 E 0 minus P over 2 epsilon 0 in the y direction. Since everything is in the y direction, I can therefore write P is equal to chi e epsilon 0 E 0 minus chi e P over 2. So, the equation now I have is P is equal to chi e epsilon 0 E 0 minus chi e P over 2, and that gives me P 1 plus chi e over 2 is equal to chi e epsilon 0 E 0, or P is equal to 2 chi e over 2 plus chi e epsilon 0 E 0. Notice if chi e is 0, then there is no P. Okay. So, now I can put the vector sign P is going to be in the y direction. The electric field E inside is nothing but E applied, which is E 0 minus P over 2 epsilon 0. So, this is going to be E 0 minus chi e over 2 plus chi e E 0 in the y direction. So, this comes out to be 2 over 2 plus chi e E 0 in the y direction. What about the displacement? Displacement is nothing but, either I can directly write 1 plus chi e epsilon 0 E, or I can use the relationship epsilon 0 E plus P, which is all the same thing. So, this is going to be 2 times 1 plus chi e over 2 plus chi e times E 0 epsilon 0 in the y direction. Next, question number 7. This is actually making use of a known relationship to find an integral. So, we are looking at the field of a long solenoid and use that to calculate a particular integral. So, consider a long solenoid. It has a field inside B in is equal to mu 0 k z, where k is the surface current. If r is the radius of the solenoid, then on the basis of this fact and Biot-Savart law, the value of the integral. So, we want to use this to find the value of the integral dz prime minus infinity to infinity integral d phi prime 0 to 2 pi, and I have r minus r cosine of phi minus phi prime divided by z prime square plus r square minus 2 r cosine of phi minus phi prime raised to 3 by 2. There is a typographical error in the assignment that we gave. Instead of z prime, we have written z out there. So, correct that please. This value is for both r less than r or r greater than r. We want to find this. Now, according to Biot-Savart law, B is nothing but integral of mu 0 over 4 pi integral. If there is a current I can even write I dl prime cross r minus r prime over modulus r minus r prime cubed. This is also equal to mu 0 over 4 pi integral j r prime cross r minus r prime over r minus r prime cubed d volume prime. If we calculate this integral written here and show that it comes to this form, that is what the integral value we want to calculate, then we can relate, we can find the value of this integral relating this to the value calculated through Ampere's law. So, let us do that now. What I will do in this problem is, since this is translationally invariant in the z direction, no matter at what value of z I calculate, the magnetic field is going to be the same. So, I will calculate magnetic field at z equal to 0, which makes my life a little easy. So, let us see, we are looking at this solenoid and we are trying to find B for this at z equal to 0 at some r, which is equal to mu 0 over 4 pi integral j r prime cross r minus r prime over r minus r prime cubed d v prime. Let us see what the current density is. The current flows only on the surface, and therefore, I can write current density j r prime, which is in the phi prime direction. So, this is going to be k delta, I will use cylindrical coordinates s minus r or s prime minus r, where s is the cylindrical coordinate radial direction, delta s prime minus r, and this is going in phi prime direction. R vector, we are taking z equal to be 0. So, this is nothing but r s. R prime vector is going to be s prime in the s prime direction plus z prime in the z direction. And therefore, I can write B at z equal to 0 and some s and phi is equal to mu 0 over 2 pi, k comes out, integral delta s prime minus r phi prime unit vector cross r, which is r s minus s prime unit vector minus z prime z unit vector divided by, now the distance is going to be z prime square plus this r s unit vector minus s prime unit vector distance, which is s prime square plus r square minus 2 s prime r cosine of phi minus phi prime raised to 3 by 2. This is easy to see, the distance that I just used. If you look at s and s prime, and we are actually looking at a distance here, take an x and y components and you will get this answer. So, I can do the s prime integral right away and write this as mu 0, oh, how did this 2 pi come, this 4 pi, mu 0 k over 4 pi integral phi prime cross r s minus s prime will now will become r s prime unit vector minus z prime z divided by z prime square plus r square minus 2 r r cosine phi minus phi prime raised to 3 by 2, and I am left with only d phi prime r times dz prime integral, the volume integral. I should have written that here also, because the volume integral is nothing but ds prime s prime d phi prime dz prime. ds prime we have already integrated over, so that s prime gets replaced by r. Now, I know that final b is in the z direction. Phi prime cross s is in the same x y plane, is going to give me a component in the z direction. Phi prime cross s prime again is going to give me a component in the z direction. However, phi prime cross z is going to give me a component in the x y plane, and that should integrate to 0, because final b on the left hand side is in the z direction. So, the last term, this does not contribute to the integral at all. We can immediately see that if I write this integral with z prime, I know that the answer is going to be 0, because on the left hand side there is no component in the x y plane. So, I am left with b, which is mu 0, let me write it, mu 0 k in the z direction is equal to mu 0 k over 4 pi integral dz prime from minus infinity to infinity, integral r d phi prime from 0 to 2 pi times phi prime cross r s minus r s prime divided by z prime square plus r square minus 2 r r cosine of phi minus phi prime raised to 3 by 2. Let us see what phi prime cross s is. So, let us look in this x y plane. Let us say this is s prime, this is phi prime, and this is s. This angle is phi prime, and this angle between s and s prime is phi minus phi prime. So, at this point, this is s, this is phi prime. The angle between s and s prime unit vector is phi minus phi prime, and therefore, angle between phi prime unit vector and phi unit vector is also out here. Let me show it in a different color, is phi minus phi prime, and therefore, this angle is pi by 2 minus phi prime. And now, you can see that unit vector phi prime cross s is going to be in the z direction going into, so minus z direction, sine of pi by 2 minus phi prime. So, that is going to be cosine of phi minus phi prime, and phi prime cross s prime is equal to phi prime cross s prime, you can see is phi prime cross s prime is minus z, and therefore, the right hand side in the above becomes is equal to mu 0 k over 4 pi integral minus infinity to infinity dz prime 0 to 2 pi r d phi prime. Inside I get r minus r cosine of phi minus phi prime in the z direction. So, I can now remove z unit vector and write mu naught k on the left hand side divided by z prime square plus r square minus 2 r r cosine of phi minus phi prime raised to 3 by 2. The rest of the things are simple. I can cancel mu naught k on the two sides, and this is only for r less than r. For r greater than r, there is no field, so it has got to be 0, and therefore, the answer I have is therefore, that integral minus infinity to infinity dz prime integral d phi prime 0 to 2 pi, all that I have written is going to be 4 pi over r for r less than r and 0 for r greater than r, and that is the answer. Next, question number 8. A disk with its center at the origin, therefore, this is the z axis, carries a uniform surface charge density sigma and is rotating with angular speed omega. Then the magnetic field on the z axis at height h is going to be. What I can do this problem is divide this disk into small rings of width delta r. Calculate the magnetic field delta B due to each ring and then add it up. So, I will calculate the field due to this ring at height z. Now, I know if I have a ring of radius r with current I, then at height z, the magnetic field due to this is nothing but mu 0 I over 2 r square over r square plus z square raised to 3 by 2, and it is in the z direction. In the present case, this I is going to be corresponding to the I due to this ring. So, let us do that now. So, if I look at this disk, take a ring of thickness delta r, radius r, then the current I is the charge passing per unit time. The charge in this ring of width delta r is going to be its area 2 pi r delta r times sigma, and per second this charge passes omega over 2 pi times or the frequency times. So, this is equal to sigma r delta r. This is the current in this ring, and therefore, that small delta B due to this is going to be mu 0 over 2 sigma r delta r times r square over r square plus z square raised to 3 by 2, and total B, which is in the z direction at height z, therefore, is going to be mu 0, or there is an omega also, sorry, there is an omega, mu 0 sigma omega divided by 2 integral 0 to r cubed dr over r square plus z square raised to 3 by 2. And this integral is very easy to calculate. You can calculate many different ways, but let us see. I can write r equals z tangent of theta, or I could also do some other substitution. Then dr becomes z secant square theta. Then I have B equals mu 0 sigma omega over 2 integral theta equal to 0 to tan inverse r over z. R cubed will become z cubed tan cubed theta. This is z secant square theta d theta divided by z cubed secant cube theta. Let us cancel a few terms. Z cube cancels, secant square theta cancels, gives me sec theta, and this therefore, this becomes mu 0 sigma omega over 2 0 to tan inverse r over z sin cube theta over cosine square theta d theta. This is an easy integral to calculate. I can write this as equal to mu 0 sigma omega over 2 integral 0 to tan inverse r over z sin square theta over cosine square theta sin theta d theta, which I will write as d of cosine theta with a minus sign in front. Now, we take cosine square theta to be x square. So, this becomes minus mu 0 sigma omega over 2. At theta equals 0, cosine theta is 1. At theta equals tan inverse r by z, cosine theta is z over square root of r square plus z square. I have 1 minus x square over x square dx, where x is cosine of theta. So, this is equal to mu 0 sigma omega by 2 z over square root of r square plus z square to 1 dx 1 over x square minus 1. I have changed the minus sign and changed the limits. So, which is mu 0 sigma omega by 2, inside I have minus 1 over x going from z to square root of r square plus z square to 1 minus x z over square root of r square plus z square to 1. And this gives me mu 0 sigma omega by 2 minus 1 minus minus plus square root of r square plus z square over z minus 1 minus minus plus z over square root of r square plus z square. So, that the answer becomes mu 0 sigma omega by 2 r square plus 2 z square over square root of z r square plus z square minus 2, and there is a z outside also. Let us see, there was a z here. So, this z remains here, 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 this z comes here, z comes here, and this is your answer. This z then cancels, I can cancel this with this, and this is 2 z, and that is my answer. Next, problem number 9. Consider a thin solenoid of length L. We have a thin solenoid of length L and radius A. L is much greater than A. So, that when I turn it into a toroid, a ring shape, then this radius r is much greater than A. It is bent into a ring, so that it becomes a toroid, which is kept with its center at the origin. So, this is the origin, and its axis being the z axis. So, z axis is coming out of the screen, and the magnetic field in it is in the phi direction. So, this has a magnetic field going in the phi direction. The solenoid carries a current I. So, it carries a current I and has n turns. So, it carries a current I and has n turns. So, that the number of turns per unit length is n over L. Okay. taking into account the similarity of the equations of, we want to take into account the similarity of equations of curl of B is equal to mu naught j and curl of A is equal to B. Find the vector potential for this toroid on the z axis at height z. So, let us see, I am going to map this toroid with this B field going around in the phi direction. Make this similar to a ring with current I going around in the phi direction and the corresponding B. Since the underlying equations are the same, the equation for B is going to be the same as equation for A, with mu naught j and B playing similar roles. So, let us see now, if I have a ring which carries current I, all right. Now, if I solve for B, del cross B equals mu naught j, then B on the z axis is in the z direction and it is given as, we have already seen it just now, mu naught I divided by 2, radius being r square, r square plus z square raised to 3 by 2. What is I? I is nothing but j dot dA. Now, let us look at a similar situation for this toroid in which there is this B field going around and I have del cross A equals B. So, I can write that A should be in the z direction as a function of z on the axis and it should be, there is no mu 0, I will be replaced by now B dot dA, which is the flux. So, flux through the ring divided by 2 times r square over r square plus z square raised to 3 by 2. What is the flux? Now, rest is all keeping the values in. So, flux is nothing but pi A square, which is the cross section of the solenoid, times the B field there, which is pi A square. B is nothing but n over L times I. So, this becomes pi A square n I over L. R square is going to be L over 2 pi square divided by L over 2 pi square plus z square raised to 3 by 2. The rest is all algebra and you can calculate your answer. I must add here that I think the answers that we have given in the assignments are missing a factor of pi square or something. Please check that. So, let us just work it out and see what it comes out to be. It comes out to be pi A square n I L square over 4 pi square L times L square plus 4 pi square z square raised to 3 by 2 times 8 pi cubed. And there is a factor of 2, there is a factor of 2 here. So, this 8 cancels, pi square cancels with this and I get a pi square, this L cancels with L. So, the final answer that we get here is pi square A square n I L over L square plus 4 pi square z square raised to 3 by 2. And I think then therefore, I am missing a factor of pi square in the answers that we gave in the assignment. Finally, the last problem which says that magnetic vector potential of on the z axis of this disk which is rotating with omega and carries a charge sigma will be. We want to use the equation del square A equals minus mu naught j. In this case, we have already figured out j is going to be only the surface current k, which is nothing but sigma 2 pi r delta r, which is the current being carried by this ring at distance r from the center, divided by delta r times omega over 2 pi is going to be j is in the phi, or k, which is in the phi direction. So, this is going to be this 2 pi cancels, delta r cancels, you get sigma r omega in phi direction. Now, using the Poisson's equation, del square A equals minus mu naught j, and therefore, del square A x is minus mu naught j x, and del square A y is minus mu naught j y. You can see that A should be in the direction of phi itself, because j is in the direction of phi. But on the z axis there is no uniquely well defined phi, and therefore, A on the z axis is going to be 0, and that is your answer. So, this completes assignment 4 for us.